Our generation will get to witness firsthand a defining moment for the electronics industry. Its MVP, the conventional transistor, is on its last legs and struggling to keep up with modern technology. In my last speech, we investigated the conventional transistor and saw some of the fundamental limitations that it was approaching. We also talked about the implications that this may have on future advancements. We saw that the electronics industry was in dire need of a new circuit element to take over. With its smaller size, comparable electrical behavior, and simpler fabrication process, the carbon nanotube is a viable substitute for the outdated conventional transistor. Having a sister who's been researching carbon nanotubes at MIT for the past few years, I've been exposed to these fascinating circuit elements for quite some time now. In this talk, we'll discuss why nanotubes are a feasible substitute for the outdated conventional transistor, and we'll look at three major categories for this. First, we'll look at the size and structure of the carbon nanotube. Next, we'll see some of its implementations in circuitry, and finally, we'll see how it's fabricated or manufactured in the lab. All the while, we'll compare it back to the conventional transistor that we looked at last time and see how they measure up to one another. So many of you have probably heard the terminology carbon nanotube before, but what exactly does that mean? Well, the first part of the name nanotube comes from the nano-sized diameter of the device. According to Gallagher and Dawsey, a prominent electronics patenting firm, the size of a small carbon nanotube is about 5 nanometers across. And to put that into perspective, that's about 10,000 times smaller than an average human hair. Also, in contrast, we talked about the conventional transistor last time, which is shown in green here. And the small ones on the smaller side of the spectrum for the conventional transistor are about 25 nanometers to 50 nanometers. So you can see there's a pretty big size difference, and space is a very big-time commodity on circuit boards. There isn't much of it. Also, the second part of the name nanotubes comes from the tubular or cylindrical structure of the device. In your high school chemistry class, you learned about graphite, which is just carbon in a sheet layer, and your pencils have lots of these just sheets of graphite that come off when you write. However, if you just took one of them and rolled it up into a cylinder, that's essentially what a carbon nanotube is. Granted, that's not how they're made in the labs, but it gives you a pretty good visualization of what it actually looks like structurally. So now that we know a little bit about the size and structure of the carbon nanotubes, let's look at how they're used in circuitry. Like conventional transistors, nanotubes can be implemented as logic switches. Now, I understand that they don't look very much like the conventional transistor we talked about last time, and the fact of the matter is they don't even act very much like it either. However, researchers such as Chong-Wong Zhu, a fellow at Stanford University, noticed that carbon nanotubes can be made to act like field effect transistors that we looked at last time. Also, according to a report done by Richard Martell, a leading researcher at IBM, carbon nanotubes can be made into switches, which we can then use as logic gates, which we can use on our circuit boards, and that's what we want to use them for. So let me explain that a little bit further. Last time we looked at the conventional transistor, it had 3 terminals. So it had the source where the electrons flow in, it had the drain where they exited out, and the gate which regulated the current flow, like the drawbridge. This time we can make a similar device out of 3 nanotubes. If you look at the top picture over there, we'll have the first nanotube, and it will be negatively charged. Then we'll have a middle nanotube, which I'll call the second one, and that'll be positively charged all the time. And then we'll have a third one, and that'll be the gate. That can be either positive or negatively charged. Now, if you put a positive charge on the third one, you can see it'll make the second one bend towards the first one, and they'll touch. And that'll be the on state. So electrons will be able to flow through the first to the second, and that's the on state. However, if the third one is then negatively charged, it will bring the second one back towards it, bend it away from the first one, and they will not touch. It will be in the off state. So this is essentially how we switch out of carbon nanotubes. It's quite simple and quite amazing. Okay, so now that we know that they have a smaller size and comparable electrical behavior to the conventional transistor, they're already a more desirable substitute. However, what makes them even more attractive is their amazing fabrication process. Carbon nanotubes are grown rather than actually constructed, making the process much, much simpler. In a phone interview I had with my sister, Courtney Schmitt, she described to me the process that she goes through to grow these nanotubes in her lab. And I think to make it easier, what I'd like to do is relate it back to something we're probably more familiar with, which is an arts and crafts example. So what they do is they take what's called the substrate, which is shown down at the bottom there. That's just your base. So for them it's like silicon or something, and for us it could be construction paper. And then what they'll do is they'll take a catalyst, which would be a type of metal like iron or tungsten, and they'll put it down on the substrate wherever they want the carbon nanotubes to eventually grow. So for us, that could be glue. We could put glue there. Now what they'll do is they'll release a gas into the system that's typically a hydrocarbon, such as ammonia, CH4, because the carbons will then deposit onto the catalyst wherever it's laid down. So for us, the gas could be glitter. So you pour the glitter down onto the glue on the cardboard paper or the construction paper, and then you dump it off, and it only stuck to where the glue was. That's essentially how they make carbon nanotubes. You lay the catalyst where you want them in the defined spots, then you release the gas into the system, and then it exits out, and what's left is just carbon nanotubes where you lay down the catalyst. It's pretty cool. The entire process takes between 4 and 30 minutes, so it's also quite quick. It's not a very lengthy process. And another advantage that carbon nanotubes have is that they're made out of one of the most abundant elements on the planet, carbon. This is in contrast to other electronic circuit elements that are made out of gold or silver, platinum, or copper. Much more expensive and much harder to get your hands on. As you can see, it's made out of carbon. It's very easy to come across. So now we've talked about the 3 major reasons why, arguing for why, carbon nanotubes should be a better substitute than the conventional transistor that's already in use today. Let's recap all we've learned. We've looked into the size and structure of the carbon nanotube, then we moved on and talked about how it could be used in circuitry and how it's fabricated in the lab. Since carbon nanotubes have a smaller size, comparable electrical behavior, and a simpler fabrication process when compared to the conventional transistor in use today, they should be a candidate to replace it in the future. Now, although carbon nanotubes possess a wide array of advantages over the conventional transistor, research in this field is relatively scarce and inconclusive at the moment. There haven't been many studies done, and in fact, some studies that have been done say that carbon nanotubes may pose health risks to those that work with them. As such, manufacturers are reluctant to switch to carbon nanotubes just yet until there's more definitive information one way or the other. However, with the imminent demise of the conventional transistor, engineers will have to turn to a new circuit element to take over and carry the torch of progress for the electronic industry. I hope you will concur after hearing my speech today that the carbon nanotube should be a leading candidate for this esteemed honor. Thank you.